Solving limit through grad and undergrad perspective. So we have this limit from x, where x tends to 0, 1 minus x cot x over x squared. So basically we can solve this limit from L'Hopital's rule as well as digamma function, and we are going to solve both of them in this video. Yeah, let's begin. Okay, so first of all, we are going to solve this problem through L'Hopital's rule. Basically, in L'Hopital's rule, if we have a limit x tends to 0, f of x by g of x, this limit is also equals to f dash x by z of x if this is either in the form 0 by 0 or infinity by infinity. If it is in this form, then this limit is also equals to limit x tends to 0, f dash x by g dash x. So we are going to use this property from L'Hopital's rule. First of all, we change cot to cos in sine, which gives us limit x tends to 0, sine x minus x cos x over x squared sine x. Now we see that this is in the form of 0 by 0. It's in 0 by 0 form, due to which we take the derivative of numerator and denominator. If we take derivative of numerator, we get cos x minus cos x plus x sine x. And in the denominator, we get 2x sine x plus x squared cos x. Now we know that limit x tends to 0, sine x by x is actually equals to 1. So using this limit, we can take x to other side, which gives us limit x tends to 0, sine x is just equals to x. Using this property, we can change sine x to x over here, and we will get limit x tends to 0, x squared by 2x squared plus x squared cos x. Now we can cancel these x squares that we are seeing over here to get limit x tends to 0, 1 by 2 plus cos x, which gives us 1 by 2 plus cos 0 is 1, so 1 by 3 is the answer for this problem, which has a nice solution over here through L'Hopital's rule. The next way is through digamma function. So we have this limit x tends to 0, 1 minus x cot x by x squared. So before going to solution by digamma function, let me give you some ideas about digamma function. Basically, digamma function is the derivative of log of a gamma function, and we need to know some of its properties, such as digamma of x plus 1 is equals to a negative of Euler-Mascheroni constant plus adds x. So this one is an important thing to know, and this also implies the other formula, which is digamma of x plus 1 is equals to negative of Euler-Mascheroni constant plus summation from n equals to 1 to infinity 1 by n minus 1 by n plus x. This thing over here is actually x, so we have replaced by that. The next property is digamma function of x plus 1 is equals to 1 by x plus digamma of x, which is actually evident from this formula itself. So this formula is giving us this one as well as the other one over here. Yeah. And now with this property we are good to begin, but before we begin we have to know other formula as well. Digamma of 1 minus x minus digamma of x. This is a reflection formula which we can derive from the reflection formula for gamma function itself, we can just take log and then differentiate to get this formula. Is equals to pi times cot n pi. You can see this is more similar to pi by sine n pi for gamma function. Yeah. Now we would want to use these functions, and basically we want to have here n pi. Yeah. So let us substitute x as pi u. Yeah, pi u, so that u equals to x by pi, and thus as x tends to 0, u also tends to 0. So we have limit u tends to 0, 1 minus pi u cot pi u by pi square u square. Now we can take pi square out, and we also want to cancel this u, since we have taken it to pi times cot pi u, this form over here. So we'll divide by u as well. So we get 1 by pi square, limit u tends to 0, 1 by u minus pi cot pi u by u. And now we can change this by this formula. We get 1 by pi this one is u only, not u square. Yeah, well, pi square. So we have limit u tends to 0, 1 by u, and then 1 by u minus this one is I'm extremely sorry for what happened. This happens, but it isn't a thing to worry. Yeah, now again continue. Okay. So we had over here 1 by yeah, I actually divided by u, so we have 1 by u over here, and then 1 by u minus pi cot pi u. Yeah, this is where we were. Now 1 by pi square, limit u tends to 0, 1 by u, and then we can replace this thing by over this thing. This gives us gamma of 1 minus u minus, sorry, digamma of u, not gamma, it's digamma. Now this thing gives us 1 by pi square, sorry, pi square, the limit u tends to 0, and then 1 by u, and then 1 by u plus digamma of u is actually digamma of u plus 1. Digamma of u plus 1, yeah, we had this over here, and then minus digamma of 1 minus u. Now we'll use this formula over here as well. So that formula gives us digamma of 1 plus u as negative of Euler masculine constant plus summation from n equals to 1 to infinity 1 by n minus 1 by n plus u. And for 1 minus u, it gives us, we have to substitute u by negative u, negative of Euler masculine constant plus summation from n equals to 1 to infinity 1 by n minus 1 by n minus u. Now if we subtract this 2, we are going to get, yeah, up to this one, we will get 1 by pi square, limit u tends to 0, 1 by u, and then we will have summation from n equals to 1 to infinity 1 by n plus u minus 1 by n plus u. Alright, yes, this is the thing we'll get. Now we will have 1 by pi square, limit u tends to 0, 1 by u. If we sum this, we get summation from n equals to 1 to infinity n square minus u square and then n plus u. Oh, sorry. This one over here, I think it's n minus u, not n plus u. It's n minus u. And then we get n plus u minus n plus u again. So that's 2u. Yeah, n plus u minus n plus u, 2u. And then we can, this sum is for n, we can take 2u out as constant, which gives us 1 by pi square, limit u tends to 0, yeah, 2u by u, and summation of n equals to 1 to infinity 1 by n square minus u square. We cancel this u out, and then we have 1 by pi square. Actually, we can take 2 out as well. 2 by pi square, limit u tends to 0, summation from n equals to 1 to infinity, and then 1 by n square minus u square. Now we can put the value from the limit, which gives us 2 by pi square times summation from n equals to 1 to infinity 1 by n square minus 0 square. So now this is just a Riemann zeta function for, we were around the end, but it just left us. Okay, but we are around the end. It doesn't matter. So we have, yeah, n equals to, okay, so n equals to 1 to infinity. Oh, sorry. I had no intention to do that. So n equals to 1 to infinity 1 by n square minus u square. So this is 2 by pi square, and if we substitute u as 0, this is just zeta function of Riemann zeta function of 2, which is pi square by 6. So 2 by pi square times pi square by 6. So this is 1 by 3, as we got earlier from L'Hopital's rule. So you see, and doesn't matter, I'll leave it. So 1 by 3, let me write it, 2 by pi square times pi square by 6. Okay, so we got 1 by 3 again from diagonal function as well. We used some of these formulas of diagonal function very nicely, and yeah, both of the solutions are equally elegant. But since if we know something exists, we can definitely try something different to get a simple answer, but through a ridiculously weird way. Yeah, that is what I wanted to show. Hope you enjoyed the video. Thanks for watching. Look forward to seeing you in the next video.